For this video, we're going to take a look at the convergence of summation, or to study the convergence or divergence of summation n equals 1 to infinity, 1 over n, 1 plus the natural log of n quantity squared. As it turns out, the only technique that we've learned in class that's going to apply for this one is the integral test. So we employ the integral test. Okay. To do this, we'll let f of x equal to 1 over x times 1 plus the natural log of x squared. Now, to employ the integral test, we have to check three things. Now, I'm not going to make a big production about checking every dot and tittle about each of these three things, but they certainly should be mentioned. Number one, f is positive, and we're going to be taking this in the range where x is greater than or equal to 1. If x is greater than or equal to 1, then f is a positive function. X is positive if x is greater than or equal to 1. Natural log of x is greater than 0, so 1 plus that's going to be greater than or equal to 1. Whole thing's positive. Number two, f is continuous. The denominator here is positive. Natural log is positive. Natural log is continuous. X is continuous. Whole thing's continuous. I'm never dividing by 0. And number three, and this one takes the most work, f is decreasing. And to study that f is decreasing, we will check the derivative to make sure that the derivative is negative. So if I take the derivative of this function, and let me rewrite this as x plus x times natural log of x squared to the negative 1. Okay, so if I take the derivative, I get negative of the thing in brackets to the minus 2 times the derivative of the inside, which is 1 plus, okay, then a product rule here, derivative of the first times the second plus the first times the derivative of the second. Now, I could simplify this. However, I don't need to. The only point is to see is if this thing is negative. Everything here is positive. Positive to the negative 2 power is still positive. Over here, everything is positive if x is greater than or equal to 1. So I have a negative times a positive times a positive. That is negative if x is greater than or equal to 1. Okay, and so that checks that f is decreasing. Okay, so we have that it's decreasing, and so now we apply the integral test. We calculate the integral from 1 to infinity of dx over x times 1 plus natural log of x squared. Now, if this diverges, then the original sum, which I've got it back on screen here, if the integral here diverges, then the original sum diverges. If this converges, then the original sum converges. Okay, now this is a indefinite integral, so let's set this up with our limits. Limit as b goes to infinity of integral 1 to b of dx over x times 1 plus natural log of x squared. Okay, now we employ a substitution. The substitution that we will use, we will let u be equal to natural log of x. With that substitution, du is equal to 1 over x times dx. The endpoints, if x is equal to 1, then means u is equal to the natural log of 1, which is 0. And if x is equal to b, then that means u is equal to the natural log of b. And so employing the substitution, we get the limit as b goes to infinity of integral from 0 to natural log b using the new endpoints. Dx over x becomes du, and then what's left is 1 plus u squared. Okay, now this is off our standard list of integrals. So this is equal to the arctangent of limit as b goes infinity, bad habit. Limit as b goes infinity of the arctangent of u evaluated from natural log b to 0. So limit as b goes to infinity of the arctangent of natural log b minus the arctangent of 0. Okay, now to do this, we will again use a standard formula that we should have down. And that standard formula is that the limit as x goes to infinity of arctangent of x is equal to pi over 2. That's the asymptotic behavior of the arctangent function. Over here, as b goes to infinity, natural log b blows up. And so arctangent of something that's blowing up goes to pi over 2. And so this works out to be pi over 2 minus the arctangent of 0, which is 0. And so that is equal to pi over 2. And therefore, the series converges by the integral test. Not so much that this is equal to pi over 2, but that it's equal to something. This integral converges, and it happens to converge to pi over 2. So because this integral converges to something, we can conclude that the original series, sorry, I got that covered up. The original series also converges. Okay, so that's the problem, or that's the end of the solution. If you want to stop the video here, you are more than welcome to. You'll notice this video is going to go on for quite a bit longer. I thought for the sake of review, I would go over why the other tests that we have developed in this class don't work for this one. So this is strictly for review purposes. I'm not going to expect you to do this on the exam. Certainly, I don't want you to do this on the exam because it would take too long. But you may have attempted to use like the ratio test or the direct limit comparison test for this, and it would not have worked. And so what I want to do for the sake of the review is to go over why the other techniques don't work for this one. Okay, so the ratio test does not work. And let's go over why it does not work. To try the ratio test, we would need the limit as n goes to infinity of 1 over n plus 1 times 1 plus natural log squared of n plus 1 all over 1 over n times 1 plus natural log squared n. Okay, so let's start working on this. So that's the limit as n goes to infinity of n times 1 plus natural log squared n over n plus 1 times 1 plus natural log squared of n plus 1. And we can get started on this by noticing n over n plus 1. That's a rational function. The leading coefficient, the leading exponents are the same, so it would just be 1 over 1, so that's just equal to 1. So we can make this limit a little bit simpler, recognizing that the limit as n goes to infinity of n over n plus 1 is equal to 1. And let me copy down the next line, or everything else that's left over. All right, now for this, we have to use L'Hopital's rule because this has the form infinity over infinity. So applying L'Hopital's rule, we would get limit as n goes to infinity. The derivative of the top is 0 plus 2 times natural log n times 1 over n all over. Derivative of the bottom is going to be 0 plus 2 times the natural log of n plus 1 times 1 over n plus 1. And so we get limit as n goes to infinity of n plus 1 over n. If I work these, the 2's cancel. And then I have what's left is going to be natural log of n over natural log of n plus 1. Now, once again, this limit is equal to 1, and so that can be just simply dropped. So I get natural log of n over natural log of n plus 1. All right, once again, this has the form infinity over infinity. And so we get the limit as n goes to infinity of 1 over n all over 1 over n plus 1. And so that's going to be equal to the limit as n goes to infinity of n plus 1 over n, which is equal to 1, which is really unfortunate for all that work we just did. If this had proven to be less than 1, then the series would have converged. If this was greater than 1, we could say diverge, but it's equal to 1. So if this limit works out to be equal to 1, the ratio test is inconclusive. So the ratio test is inconclusive. And so that will not work, unfortunately. All right, let's try it again. Except this time, let's use the root test. As it turns out, the root test does not work either. Let's see what happens. Limit as n goes to infinity, 1 over n times 1 plus natural log squared n. And let's take the whole thing to the 1 over n power. So this is the limit as n goes to infinity, 1 over n to the 1 over n. And what's left will be 1 plus natural log squared of n to the negative 1 over n. Okay, well, this is promising. N to the 1 over n, I know the limit of that. That goes to 1. And what's left is 1 plus natural log squared n, negative 1 over n. So I'm using the limit. So I'm using the fact that the limit as n goes to infinity of n to the 1 over n, I know that limit is equal to 1, and so I'm employing that result going here. Okay, so what's left is now going to be 1 plus natural log squared n to the negative 1 over n. This now has the form infinity to the 0. As n goes to infinity, the bottom blows up. As n goes to infinity, this exponent goes to 0. And so this is going to be the form of L'Hopital's rule. So let's let L be equal to this. Then natural log of L will be equal to the limit as n goes to infinity of the natural log of this expression using the fact that natural log is continuous. Okay, now the negative 1 over n comes out. So the limit as n goes to infinity of negative natural log of 1 plus natural log squared n over n. Okay, this now has the form infinity over infinity. And so I apply L'Hopital's rule. Limit as n goes to infinity. Let's start with the easy one. The derivative of the denominator is 1. Okay, I like that. On top, it's a mess. The derivative of negative natural log of something is going to be negative 1 over the something times the derivative of the inside, which is going to be 0 plus 2 times the natural log of n times 1 over n. Okay, and so we get the limit as n goes to infinity of, let's see what we get. We get negative 2 times the natural log of n over n times 1 over 1 plus natural log squared n. Okay, at this point, I could use L'Hopital's rule again. However, I have a standard limit here. The limit as n goes to infinity of natural log n over n, I know that is equal to 0. That's something that we've done before. Logarithmic growth is slower than polynomial growth. And so I know and I can verify that by L'Hopital's rule directly, I know this limit is equal to 0. Furthermore, this limit is also equal to 0. 1 over 1 plus natural log n squared. The denominator here blows up. So 1 over something that blows up, this also goes to 0. So this is equal to 0 times 0, which is 0. So the natural log of L is equal to 0, and therefore L is equal to e to the 0, which is 1. Now, once again, this is extremely unfortunate. If this number had been less than 1, then I can conclude the series converges. If this number was greater than 1, I can conclude that it diverges, but it's equal to 1. And so we conclude the ratio test is also inconclusive. I cannot tell if it converges or diverges based on the ratio test. Okay, so let's try something else. Next thing we could try is the comparison test. So the comparison test does not work. Okay, well, let's see. 1 over n, 1 plus natural log squared n. I can find something that's bigger by getting rid of this, and so that's less than 1 over n. I've made the denominator smaller, which makes the fraction bigger. Okay, so, and I also know that this diverges, that the sum of 1 over n diverges. But this tells me nothing about whether or not the original sum converges or diverges. Okay, so if this had converged, then I can conclude this converges. However, if the bigger thing diverges, the smaller thing could either converge or diverge. So to use the comparison test, I would need to make this less than something that is convergent. And there's no obvious way to make that work for this particular example. So the comparison test does not work. Okay. Now, the last thing we could try is the limit comparison test. Now, the obvious thing to compare it to is 1 over n. So let's see what happens. Limit as n goes to infinity of the original function, or the original nth term, divided by 1 over n. Okay, so the 1 over n's cancel. So we get 1 over 1 plus natural log squared n. Okay, now this blows up. So 1 over something that blows up, that's equal to 0. Now, again, that's kind of unfortunate. We cannot make any conclusions about this. That proves that since one of the summation 1 over n diverges, we can make no conclusions about the original series. If this had been anything other than 0, if it had been any positive number or the interval was infinity, then I can conclude that the original series diverged. However, if I do this test and the bottom diverges and this limit proves to be 0, then I cannot conclude anything about whether or not the original series converges or diverges. Okay. As I said before, and I'll repeat again, the 4 illustrations that I just did showing how the other tests do not work, I do not expect you to do that on the test. This was strictly by way of review to explain how to use those tests and how to see that those tests do not apply to this particular series. The way to solve this problem was the first method, which was the integral test.